Assalamualaikum warahmatullahi wabarakatuh and good day to everyone. So welcome back to this course, BMFG 1213 Engineering Materials. Alright, previous lecture we have learned the process of diffusion. We also know the state of diffusion and we know some of the factors that affect the diffusion in solids. We also discussed on the application of this diffusion in some of the industry. So now we continue our lessons in chapter 6, which is mechanical properties of metals and alloys. Alright, before I start, I would like to emphasize our course learning outcome for this course. Okay, by the end of these 14 weeks classes, you should be able to grasp all these three course learning outcome. And our chapter for this week, which is mechanical properties, will correspond to this CLO number 2, which is analyze the properties of engineering material based on its structure. Let us look at the learning objective for this chapter. So we have about eight learning objective. So for this week, week 6, we will cover these 3 LO, right? Which is define engineering stress and engineering strain. Basically, your engineering stress denote as sigma, right? And your engineering strain denote as epsilon. So once you finish this chapter, you should be able to define what is engineering stress and engineering strain, the formulation of this stress and strain. Right, number 2, you should be able to state the Hooke's law. The Hooke's law and also the Poisson ratio, and note the condition under which it is valid. And number 3, you should be able to know the modulus of elasticity, which is your E value, modulus of elasticity, and also the tensile strength, you know as the sigma, and you know how to estimate the percent of elongation. Okay, the percent of elongation. Once we give you an engineering stress strain diagram. So basically, what you will learn later, we have this strain versus strain. So basically, you will have this kind of graph, and you should be able to know where is the E value, the modulus of elasticity, and then the tensile strength, and also the percent of elongation in the strain. Okay, so the rest, number 4, 5, 6, 7, and 8, we'll cover it during our next lessons, which is in week 7. Alright, so why do we need to understand this? Why do we need to study the mechanical properties of metal and alloy? Why? Okay, you may recall this, right? This is the tetrahedron material model. In this model, we know the relationship between the structures, properties, performance, and processings, whereby these structure will affect the properties, performance, as well as the processing. And now we study the properties, okay, these properties, which is indirectly will determine the processing that we need to do with that particular material, and also will affect the performance of that particular material. Alright, so this why it's really important to study the mechanical properties. So these are some of the classification of material properties. So we have physical, magnetic, chemical, technological, electrical, we have optical, and thermal. And for this particular chapter, which is chapter 6, we will study on the mechanical properties. So these are some of the mechanical properties that we'll be discussing in this lecture, which is strength, or plasticity, ductility of your material, the toughness of the material, elasticity, how stiff your material, brittleness and hardness. So these are the mechanical properties that we will discuss along this lecture. Okay, let us begin with the introduction of the mechanical properties, what it's all about. So mechanical properties basically involve a reaction to an applied load. Okay, it's a reflect relationship between its response or deformation to an applied load or force. Say for example, you have this kind of steel. This is your material, steel material. Then you apply loading here, say for example a compression. So you want to look this material, the response of this material or how this material respond to that particular forces that has been applied. So these are mechanical properties. Okay, so many material when in service subjected to forces and loads. For example, aluminum alloy from which an airplane wing is constructed. So why we use aluminum alloy instead of 1,000 more materials? Okay, and then another one is steel in an automobile axle. So why we use this steel in automobile axle? Is it because of the properties? Is it because it's easy to deform? Is it because of the processing? Right? So these are some criteria or characteristic that we need to know in order for us to design the application of that particular material and to make sure that the fracture or failure will not occur. Alright. The response of material to an applied forces depend on the structural arrangement of type, the nature of the bond, and the atoms, molecules, or ion. So it reflects back with the tetrahedron material model. Okay, we have this kind of model. So we have a structure, a crystalline structure, which affect the properties of that materials and also the processing. And last is the performance. So it will reflect back to this tetrahedron model. Alright, factors to be considered, which is nature, environmental, duration, how long your testing or how long the force been applied to that particular material, and then the temperature. Okay, either it's a room temperature or high temperature. It will affect the overall property. So these are some of the examples of failure that happened around the world. Okay, from structural of building or even in vehicle. We can see here ships here, a vessel. Alright, so let us look this number one, which is steel bridge. This is the steel bridge at West Virginia, December 15, 1967. So what happened here? This bridge is collapsed, right? It's collapsed. And investigations found that this failure is due to small defect, around 2.5 mm deep. And why it is happened? Because it's overloading, alright? And it's also poor maintained. Okay, so as a structural engineer, so what you need to do is you need to know how to determine the stress and stresses distribution within members that are subjected to load. So in order for us to avoid this happens, so a structural engineer will do this kind of analysis. Alright, they analyze and predict various stresses using experimental and structural analysis. So you need to analyze this stress distribution along this bridge. Another thing is in MRR2, which is happening in Malaysia, our country. So you can see here some crack happen here. And as a role as mechanical engineer, we are concerned with the development and design of machine and structure, etc. And we also need to measure the mechanical properties and why this happened, analyze and make some investigations, the root cause of this failure. Okay, for vehicles, we have some example here. Failure of Liberty ships service during World War II. So basically, this Liberty ship, this vessels is failed due to crack initiate from defect in the welded area, and this welded area is subjected to sub-zero temperature, 0 degrees Celsius. Okay, so previously I told you we already discussed some of the factors involved in failure. One of it is temperature. So these are some of the example. Because of different temperature in sub-zero temperature, it initiate the crack. The crack is initiate in a welded area, and then we as a materials and metallurgical engineer, we are concerned with producing and fabrication materials to meet service requirement as predicted by this stress analysis. So understand relation between microstructure and material and their mechanical properties, because this failure happened, one of the factors is because of the temperature. It's related to the microstructure itself. So we as a material engineer needs to analyze, needs to know and understand this relationship. Okay, now we go for other example in electric and electronic application. So here we have wire bond breaking and lift off. So wire bond are small wires that connect an integrated circuit ICs die to its lead. They are thin and fragile and can fracture under mechanical stresses. The most common failure analysis technique can be identified by X-ray microscope. So this is wire bond and breaking. And another one is capacitor cracking. So we have here MLCC, multi-layer chips capacitor. It also can be cracked. It also can having a failure under mechanical flexure or thermal shock. For example, you have this is your board, circuit board, and we have a capacitor here. We have some capacitor. It's a ceramic capacitor, and you solder here. Do some soldering. So what happened? What happened is flex cracking occurs when the board that the capacitor is soldered to experience excessive bending. So once you do some soldering process, and this board is happen an excessive bending. Okay, so this will initiate the flex cracking. Okay, so basically the flex cracking is, if you look cross-sectional area of this capacitor, so the crack will happen somewhere here inside the capacitor. Why? Because capacitor from it's a ceramic material. Ceramic material is mostly strength in the compressive stress, but not in the tension stress. So here during soldering, so this ceramic material cannot extend the tension of the solder part. So what happened? It become crack. Okay, that's we call it as flex cracking. Alright, and then it also can be caused during depaneling, connector, insertion, and then fixturing and other mechanical events. So I'll show you some of the event which is during soldering process. This excessive bending will cause the crack of this ceramic or MLCC capacitors. Alright, the other thing is thermal shock cracking occurs when the part experience a sudden dramatic temperature increase, such as improper soldering. Because in soldering, we use we play around with the temperature. So if this material is not extend to that temperature, to that particular temperature, so the sudden dramatic temperature increase, so it will cause the flex cracking. All right. Another thing is solder overstress. Solder overstress occur when a single mechanical event such as drop result in a fracture solder joint. It's almost similar with this capacitor cracking during soldering process. So what we use here, we use an optical microscope and cross-sectioning to identify which is the overstress fracture. Right, so typically cracked solder joint caused by mechanical overstress will have much larger gap. So to identify the defect on that, or the failure on that particular part, so we will look the larger gaps here compared to the other part. Okay, so this caused by solder fatigue. We call it as solder fatigue. So basically, the solder overstress is happen during the soldering process on the IC board. Okay, basically the stress strain is described on how a specimen or how a body responds to an external forces. So we want to know what happened to the body or to the specimen. So in this subtopic, we will explore details on the concept of stress strain. Okay, this can be explained during stress strain tests, whereby the load must be static, and then the change of the load must be really slow. Okay, and the load must be applied uniformly over a cross section of the specimen. Okay, so this testing normally used or conducted at room temperature, and the specimen itself is usually fractured, or we can call it a damage, or it's permanently deformed. Okay, so let us look the possible way to study this stress strain behavior. So we use 4 principles way. It's depend on the load applied. So here we have tensile. Number 1 is tensile test. Tensile means you are trying to extend the load here. And here we can see the changes in the length, which is L naught and L, and also the changes on the A. Okay, so the dash line means the original, and the fixed line here is the final dimension. Okay. Right, number 2, go for the compression test. In compression test, you are trying to compress it. It's different way, different direction for compared to tensile test. So same with tensile test, we have some changes on the A and also some changes in the L value. And number 3 is a shear stress. Shear stress where you are trying to give a shear force in different direction here. And number 4, which is your torsion test, whereby you are trying to twist the sample, twist the specimen, and see how much twisting is possible for how much twisting force, the twisting force here. So these are 4 types of loading that explain the stress strain behavior. But normally in practical application, normally we will use tensile test. So from now on, we will see the tensile test study. Okay, so this is an example of a tensile test. We use universal testing machine, or we call it as UTM machine. So here we have the equipment, basically the equipment, and this is the specimen. We use a standard tensile specimen with either circular cross section, or we also have a flat type. So it's depend on your material, either polymer or metal. Normally for polymer material, we use this flat shape, whereas the metal, normally we use this circular cross section, or we can call it dog bone. Okay, basically in standard tensile specimen, we have this kind of specimen, yeah, and the diameter, this is the diameter, is approximately around 12.8 mm, and the radius section here is around 60 mm, and also we have this region. This region we call it as a grip region. Why I say this is a grip region? Okay, this is the grip region because during the testing, this equipment will hold this specimen at this grip region. Okay, so we call it as a grip region, and most important part is the gauge length. We call it as gauge length here. Okay, whereby if this is your original specimen, we will denote this gauge length as L naught. Okay, why is really important this length? Because this length is where the actual measurement is being done. Okay, we use this extensometer here. We have extensometer. So that is why I say it's really important, because this extensometer is continuously and simultaneously measure the changes in the gauge length. Alright. Okay, so during tensile testing, the sample itself, let's say this is the original sample. When we apply the load, the gauge length is trying to elongate, right? Trying to elongate, and at certain point, they will form necking here. Okay? We call it as necking. And if we further the load, so what happened here? The sample will be fractured. But from the testing, we can develop a diagram. What types of diagram? It's a stress versus strain. Okay, where we have this sort of diagram. Okay, this is fracture, and this is your UTS, ultimate tensile strength, and you also have some modulus E, which is your E value here. So we'll discuss this later in the next lecture. But basically what I want you to know that with this testing, this tensile testing, you can have this kind of specimen, right? Start from elongation of the gauge length, and then necking process, and the specimen will break into two pieces. And you also will have this kind of diagram, which is stress versus strain. Okay, so this stress versus strain will show you exactly what is the maximum strength that this particular material will extend before it goes necking, and before it fracture. And also from this diagram, we will know the elastic formation for this particular material. Okay, based on the tensile test, we will have this kind of diagram, stress versus strain. Okay, so what is the stress formula and what is the strain formula? How we are going to calculate the stress and how we are going to calculate the strain. So stress is equal to sigma is denoted as a stress, is equal to force F over A naught. So here, if you look into this diagram, into this figure, this is the F value, and this is A, which is your area, specimen area. And for stress unit, it's referred to 1 megapascal or 10 power 6 Newton meter squared. So Newton referring to your force, which is Newton, and m squared is your area. Okay. So F is basically load applied perpendicular to the area, original cross-section area. Well, let us look at the engineering strain formula. So this is your strain, which is epsilon. What is strain? Strain is the changes in the gauge length, a specimen, divided by its original gauge length. So Li is referring to your instantaneous length, and L naught is your original length of the specimen. So the difference between these two, delta L over the original length of the specimen. Then we will have this strain. Okay, there's no unit for strain. And here, if you look into this figure, so this is the strain, tensile strain. Epsilon is equal to delta over L naught. Delta is referring to the difference between the original length and the final length or the instantaneous length. And for the lateral strain, we have this way, this lateral strain, which is epsilon L is equal to minus, minus, because the length of that lateral strain is getting decreased. That's why it's minus delta L over WO. This is WO, the original one. Now we go for the torsion test. Like I mentioned previously, in torsion test, we are trying to twist this material. And once we twist the material, we have this kind of angle. This angle, we call this as angle of twist, represent with denote as phi. And in this case, it's a function of applied torque. That's why this is T. This is represent torque. Because this torsion is a variation of pure shear, so we can use this formula, which is tau is equal to Fs, which is your shear force, over the A naught. Alright, so this structure member is twisted. This is twisted because we trying to twist the material, and then the torsional force produce a rotational motion about the longitudinal axis of one end of member relative to the other end. So this one end, this is one end, and this is another end. Alright, so it produces rotational motion, about in this longitudinal axis. Alright, normally this torsion test is performed in a cylindrical solid shaft or tube. So these are the formula. Alright, so we use the shear stress formula because it's one of the variation of pure shear. And if you look here, basically what happened, we apply some moment here, and we have a new area which is the AC, and we also measure the 2R value, which is the radius here. So note that tau is equal to M over ACR here. So I will not go detail on the formulations. I want to give you an idea what is torsion test is all about. It's also related to pure shear stress. So the angle, the shear strain, which is the gamma, is related to the angle of twist here. So it's related with this angle of twist. Let us look at some common states of stresses. Here this is the ski lift. We can see several types of stresses. The first one would be a simple tension, which has been experienced by this cable. If you can see, this is the cable. Alright, it's experienced a tensile stress. Right, and number two, which is here, drive shaft. So this drive shaft is actually twisted. It's continuously twisted in order for this wheel to move. So this drive shaft is experience a torsional stresses. Alright, and then another one, what can I give you, is this column. This column, or we call it as support pillar. This support pillar is basically experience some compression stress. Compressive stress. So these are some stresses that that exist in this ski lift. Let us look another example. Here is some simple compression example. We have this large rock. This is large rock. Or we call it as boulder, is applying compressive stresses on the rock. So it's apply compressive stress on this rock, that is support the boulder. So here we can see this simple compression test, simple compression stresses, and same goes with this bridge. This bridge, Canyon Bridge, Los Alamos. This Canyon Bridge. So here we have metal struts. it's also same, give some experience some compression, compressive stresses, while it support the upper structure of the bridge. So it's experience these compressive stresses. Okay, another examples is biaxial tension. So biaxial, as the name denote here, is bi. So it means that two axes, which is x and y direction. So basically, what happened in these pressurized tanks, the forces is experienced in this kind of directions. All right. And another one is hydrostatic compression. As the name denote here as hydro, it means something to do with water. So fish in underwater is experiencing this kind of stresses. It's hydrostatic compression, whereby this water is compressed. Okay, give some compression stresses to this fish underwater. Alright, so now we are already learned and discussed the concept of stress strain. Okay, in order for us to study this stress strain behavior, four principal ways, which is referring to the load, the types of load that being applied, which is number one, tensile, which is sigma is equal to F over A naught. And then number two, compressive, similar formula, same formula with tensile. And then we got shear stress. Shear stress is referring to tau, okay, tau. And lastly, torsion, torsion stress. So we also expose some of the examples, some common stress state. So I hope you guys understand, and we continue with our next lecture, which is in deformation. Thank you.